Hello guys, and welcome to my YouTube channel. In this video, I'm going to be going over how to predict the equilibrium of acid-base reactions. So essentially, we're going to be looking at, well, which side of the reaction does equilibrium favor? So these equilibrium arrows are telling us that there is no favored side. It is equal. But we're going to be looking at disproportional equilibrium arrows. Is the equilibrium favoring the product side, which would be represented by arrows like this? Or does equilibrium favor the reagents, where it would be depicted like this, where the larger arrow is pointed to where the reaction is favored? So we don't know yet because we haven't done the question, so let's just leave it as regular equilibrium arrows. So step one, we want to identify our acid and we want to identify our base. It's easiest to identify the base because the base is going to be our nucleophile. So how do we identify the base slash our nucleophile? This is going to be the atom with the electrons. You need electron density to be a nucleophile. So it's going to be an atom that has lone pairs. It could be neutral or it could have a negative charge. Here it is negatively charged. We have an O minus, so that would be our nucleophile. Because if we draw in the lone pairs, there's 3 sets of lone pairs. So there's 3 different sets of lone pairs that could potentially go and attack something. And now the question is, okay, well, what is it going to go and attack? Well, it's going to attack something delta plus or positively charged because opposites attract. So we have our base nucleophile, and then the base will attack something delta plus or positively charged. Why? That is just because opposites attract. So we say, okay, who's delta plus or positively charged? It's not going to be on this atom, this molecule, because we've already identified a nucleophilic atom on this molecule. So we forget about it for now. So we go to the other structure, and we ask, okay, do you have something delta plus or positively charged, something electrophilic that the nucleophile could potentially attack? So right now we have H. We have a hydrogen that's delta plus because this nitrogen does not want to be positively charged. It wants to be neutral. Right now it is positively charged because if we calculate its formal charge, it has 1, 2, 3, 4 electrons that are involved in bonding. Its valence count is 5, so valence is 5 minus 4, which would be equal to plus 1. This would be our formal charge. So the nitrogen is positively charged. It does not want to stay positively charged. It wants to regain neutrality. So to do this, well, it's sucking electrons from the hydrogen towards itself. This is how you can think about this. It's like, hey, I am angry. I don't want to be positively charged. So who is nearby me? Oh, this hydrogen. Oh, I'm going to suck electrons towards myself, leaving this delta plus positively charged state on the hydrogen. So this hydrogen is going to get attacked by something that's nucleophilic. So then I, the nitrogen, because I'm very important, will regain my neutral state. So the nucleophile goes, boom, 2 in. And the reason I say 2 in is because, well, I'm taking 1 set of lone pairs. And how many electrons are in a lone pair? Well, there's 2 electrons in a lone pair. So 2 in. And then we have a 2 up onto the nitrogen. Why 2? Well, because there's 2 electrons in this bond. And then they are going to end up on that nitrogen. So let's draw in the product. So the 2 electrons that were initially in between the nitrogen and the hydrogen are now going to be right on that nitrogen. So now the nitrogen, if we calculate its formal charge, the formal charge is going to equal the valence electrons, so 5 minus 5, because we have 1, 2, 3, 4, 5, because of the lone pair now, where it's 0, so it's neutral. And then we have plus benzene ring and an O. Those two lone pairs you can think didn't move, but now the red lone pair made a bond to the hydrogen. And then this oxygen is also neutral. So now we say, okay, well, who is the base? Well, this was our base. Hence, this was our acid because it gave up a proton. So then on the other side, on the right-hand side of the reaction, this would be our conjugate base. And this is going to be our conjugate acid. And they might also give you the information such as that this has a pKa of equal to 10. So now what does that pKa really mean? Well, it means, okay, well, how easily is this compound going to give up a proton? I'm going to make this a little bit smaller. So if you increase the pKa, this is going to decrease the acidity. So if you are not very acidic, that means you're not going to be given up very easily. If you're very acidic, so if you decrease the pKa and you increase your acidity, where if you're an acid, that means you're going to be a hydrogen that is going to be extracted by a base. That means you want to leave. So who has the lower pKa? This acid had a pKa of 7. And this acid had a pKa equal to 10. So this pKa is lower, so therefore it is more acidic, increase the acidity. And I say here, equilibrium is always going to favor the weaker side, so it's going to favor the weaker acid. Why? Well, because this hydrogen, we just established that it was very acidic. That means it wants to leave, it wants to be removed. So it's always going to be getting removed and be joining to the O. And it's going to be the OH bond instead. So it's going to favor the side with the weaker acid. So this acid is weaker, hence it's going to favor this side. And that is solely because this hydrogen is very acidic, so it wants to leave. Therefore, this guy's constantly going to be attacking it, 2 in, 2 out, and it is going to reside as these two molecules in the solution. I hope that makes sense. Let me know if you have any questions down below in the comment section. Make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. Also tell me what type of questions you want me to cover next. And yeah, slay. Have a good day. Hope this made sense.